All right, welcome back. In the first part of the section 4.1 video, we kind of established the theory, and in particular, we established what this closed interval method is for finding the absolute extrema of a continuous function on a closed interval. In this video, I just want to calculate out three examples. So I'll do all the calculations in the video. I hope it won't go too slow, but I want to just pick some. I've got a polynomial, a trigonometric function, and a logarithmic function to kind of keep the variety. So in each case, the directions are given the function and the interval, locate its extreme values, its global minimums and maximums. Our extreme value theorem says that we're going to be successful, and the closed interval method is our procedure. So we're going to take derivatives, find all critical numbers, make a table of those critical numbers together with the endpoints to select the minimum and maximum values. All right, so let's get going. Scroll up here. We'll just take the derivative of this function. It's a polynomial function. So we're going to differentiate it with the power rule. So we get negative 6x squared plus 54 times 1 plus 0. And when you want to know where a function is 0 and undefined, you got to be able to factor that. So if we factor out a negative 6 here, then this becomes negative 6 times the quantity x squared minus 9, which further factors into x minus 3 times x plus 3. All right, so I can see that there are no bad critical values. This derivative is defined for every value of x, but it equals 0 if I set that derivative equal to 0, if and only if this factored product equals 0. And there are just two solutions to that. X equals 3 comes from the first factor. X equals negative 3 comes from the second factor. No other values of x make that derivative 0. Our interval in question here is the interval from 0 to 4. Yeah, so we don't have to consider any critical values that aren't in that interval. Yeah, so the critical value negative 3 is discarded because it is not in the interval from 0 to 4. It's certainly a critical value for the function, but we're only interested in values of this function between x equals 0 and 4 right now. So we would discard any, I would call it like an extraneous critical value. Okay, so now what do? Now we make a table. We have no critical values. What goes in our table? It's always an input-output table, a little T-table, sometimes people call it. And we list any critical values that we found. We found exactly one of them. And we list the two endpoints. Those are always in there. So critical numbers always go in this table. Endpoints always go in the table. Don't forget the endpoints. And then you have to evaluate f at them. To save us a little time and keep the video short, I'm going to just tell you the answers. But always when I do this, I'm evaluating f, not f prime. It's a common error. Yeah, if you plug the critical number 3 into f prime, I already know what you're going to get. You're going to get 0. That's why it's a critical number. So you have to evaluate these things in your original function. That's the table of values that I'm making. All right, I could write that original function down here again, but maybe I'll just try to leave it in view up there. So I'm taking that thing, this f of x, just bring it down here so we can see it while I'm filling in these values. And then I'm plugging in these x values. So you can verify that f of 3, you do the computation, this is what you'd write. You'd write f of 3 is negative 2 times 3 cubed plus 54 times 3 plus 5. And check me, check my math, but I'm claiming that's 113. Likewise, f of 0 is 5, f of 4 is 93. All right, so you can pause the video and make sure you can reproduce those values. So now looking at them, can we answer the question, where is our absolute max? Our absolute max value is, well, which one of those numbers is biggest? It's 113. And it's at x equals 3. I like to say where it happens. So the maximum value of this function, absolute maximum value of this function is 113. It happens when x is 3. Where's our absolute minimum value? Smallest number in that table. It looks to me like it's 5, and it happens at x equals 0. Okay. So there's your global minimums and maximums of that cubic polynomial. Let's switch over to Desmos real quick. I've got a graph ready for us. It's always a good idea. I really want you guys in this class to explore everything graphically. So there's our cubic polynomial. I graphed it on a window a little wider than 0 to 4, just because I don't like the endpoints of the interval to be right up against the edge of the screen. The buttons get in the way, but this looks consistent with what we were just saying. It looks like the minimum y value, oh darn it, the minimum y value on that, I gotta stop touching that mouse, is over here when x is 0, and we calculated that y value is 5. It certainly looks to me like the maximum y value happens at 3, and we know exactly what that y value is. It's 113, yeah? And nothing was happening over here at this other endpoint 4. It wasn't a minimum or a maximum. If this doesn't look like a cubic function to you, it's just because we're looking at kind of a small piece of it. If I zoomed out on the plane, there's our, that looks like a cubic function. Cool, okay? So switch back to the whiteboard. Let's do a second example where we have a trigonometric function. So the idea is the exact same here. The calculus is the same. This next example might feel like it's a little bit more difficult because it's a trigonometric function instead of just polynomial. But let's see what we can do. So here we are. G of t is t plus the cotangent of t over 2. And I would like to find its global minimums and maximums over the interval from pi over 4 to 7 pi over 4. Okay, so step 1, differentiate. I hope you're going to pause this and differentiate this thing before me. You might need to go look up the derivative of the cotangent function, but you'll gain experience and get these things under your belt by just repetitiously doing them. So the more differentiation homework you do, the better you'll get at differentiation. G prime is going to be 1, and then the derivative of cotangent is the opposite of cosecant squared t over 2. And by the chain rule, I have to multiply that by a half. So there's my derivative, g prime. And I want to set that derivative equal to 0, yeah? So I want to find its good and bad critical points. So how can 1 minus 1/2 of the cosecant of t over 2 equal 0? Well, I don't know. Let's rewrite that as 1/2 times the cosecant squared of t over 2 is equal to 1. And then maybe multiply both sides by 2. I'm not as familiar with cosecant and these other trig functions as I am sine and cosine. So the cosecant squared of t over 2 equaling 2 is equivalent to the sine squared of t over 2 being 1/2. So I'm going to switch that for that form because cosecant is 1 over the sine. Yeah, so cosecant squared is 1 over sine squared. And now I'm just going to do some unit circle trigonometry. Or, well, actually, excuse me, I need to take a square root. So the sine of t over 2 is plus or minus the square root of 1/2, which I prefer to write as plus or minus 1 over the square root of 2. Okay, and now by some unit circle trigonometry, that angle t over 2, I know the angles if I sort of sketched over here for us a little unit circle real quick. You have your unit circle down where you know which angles have sine plus or minus the square root of 2. Those are things like pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those would be the angles inside of the one revolution anyway. So let me write those down. So t over 2 is either pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. We'll write more if we need, but then I'm interested in t, so I'm going to double all those. So t is either pi over 2, 3 pi over 2, 5 pi over 2, or 7 pi over 2. And the screen's not very big. Sorry about all the scrolling, but I need to always keep in mind, where am I talking about? I'm talking about angles that are at least pi over 4, but no more than 7 pi over 4. Yeah. So those are the angles that I'm talking about. That was a horrible demonstration. I don't know why I just did that. I'm talking about angles that would correspond to points on the circle between 7 pi over 4 and 7 pi over 4. All right. So what about our values down here? Which one of those satisfy that condition? Pi over 2 certainly does. Pi over 2 is an angle right there on the circle. 3 pi over 2 does as well, so we'll keep it. 5 pi over 2 is not in that range. Yeah, 5 pi over 2 is the angle, corresponds to the top of the circle, but you have to go around a full revolution. So we're going to exclude it. It's not in the interval under consideration. Neither is 7 pi over 2. Yeah, those guys are not between pi over 4 and 7 pi over 4. So it turns out that we just get two critical values. Two critical values. So hopefully we have enough room to make our table. What am I going to put in our table? I'm going to put some t values, and g of t, I'll remind you, it's t plus the cotangent, cotangent of t over 2. And what values of t are we going to look at? Well, we're going to look at those two critical values that we just determined, pi over 2 and 3 pi over 2. Yeah, and then we need to put the endpoints, pi over 4 and 7 pi over 4. For each one of those four numbers, I'm going to evaluate them in this function g of t, making sure my calculator is in radians. You will get erroneous results if your calculator thinks that these t values are degrees. So rounding things to 1 decimal place, to the nearest tenth, let me tell you what these values are, and you can verify them. Stop the video and verify them. So g of pi over 2, not g prime, but g is 2.6 to the nearest tenth. G of 3 pi over 2 is 3.7. G of pi over 4 is 3.2. And 7 pi over 4 is 3.1. All right, so looking at those things, we can see that there's our absolute max. It happens at t equals 3 pi over 2. Where's our absolute min? What's the smallest number? It looks like it's happening at pi over 2. Our absolute minimum value is 2.6 approximately. And that was happening at t equals pi over 2. So there's a second example illustrating the method. Let's switch over and enjoy our work graphically on Desmos, and then we'll do another one. All right, so where's our Desmos window? There it is. You can see it. We're just looking at a piece. I'll zoom out in a second. But I've labeled the axis. This is kind of cool on Desmos. You can even have it label the axes with those values. So we're looking at this function only between pi over 4 and 7 pi over 4. So that's our interval of interest. And what do you think? Does it look like we got it right? We said that the absolute minimum value was happening at pi over 2. So on that interval, does that look like the smallest y coordinate? It does to me. We said the absolute maximum was happening at 3 pi over 2. Yeah, that's over here. Cool. And the endpoints, pi over 4 and 7 pi over 4, corresponded to neither minimums nor maximums for this example. Nice. All right. We zoom out on that, you can get an idea of what the global behavior. It's kind of a fascinating looking function, t plus the cotangent. So it's sort of a fun picture. If you remember what cotangent looks like, it's kind of a fun exercise to try to ask yourself, why does adding t to the cotangent function do that? It's kind of cool. I like that picture. Okay, one more example. Trying to keep these videos short and focused. So let me switch back to our whiteboard. Switching in this direction takes just a little bit longer, more buttons to push, but we're back. Okay, what's the third example? Logarithm function, why not? So I want to take the function log, a natural log of x squared plus x plus 1, find its minimum and maximum values over -1 and 1. You're tired of listening to me, hit the pause button right now, finish this example, and then just scrub through all of my work and see if you get the answer right. That's the best way to watch these videos. But just do the problem yourself in silence and see if you got the answer right. All right, so here we go. What do we start with? Start with the derivative computation. So h prime, got to find good and bad critical points. H prime, derivative of natural log is, well, 1 over. So we have to differentiate this log with the chain rule and then multiply by the derivative of the inside. So writing that as a single fraction, we have 2x plus 1 over x squared plus x plus 1. Okay, so we got to think about good and bad critical points. This derivative is a fraction. We have to think about good and bad critical points. So let's think about the numerator first. So how could h prime be 0? Well, if and only if the numerator is 0, and that happens if and only if x is equal to minus a half. So there's one good critical point at x equals minus a half. What about bad ones? So h prime doesn't exist if and only if x squared plus x plus 1 is equal to 0. All right, so that's a quadratic equation. Typically, we would try to solve a quadratic equation like that by factoring. Yeah, you can take a second, try to factor that thing. It doesn't lend itself to factoring very nicely. So what do we do when we're looking for zeros of a quadratic equation and we can't factor it? I personally like to just check the quadratic formula. Yeah, if we think of this in the form ax squared plus bx plus c, the quadratic formula says that if this thing is going to factor, if it has real zeros, we should look at that discriminant, b squared minus 4ac. So in this particular polynomial, what do we get? B squared is 1 squared, and then we have to subtract 4 times 1 times 1. Well, that's less than 0. So what does all that mean? That means that x squared plus x plus 1 is never 0 for real values of x. So there are no bad critical points. So we have one good critical point. It's at x equals a half. No bad critical points because the denominator of that fraction is never 0. Cool. So it's table time. What's going in our table this time? Just 3 entries. Remember what h is. It's the log of x squared plus x plus 1. And we're going to put in the critical value that we found. And we're going to put in our endpoints, minus 1 and 1. All right, I'll let you check it out on your calculator. You can verify this stuff. Let's see if I've got my answers written down. At minus 1/2 to the nearest 10th, h of x is minus 0.3. At minus 1, h is 0. And at positive 1, h to the nearest 10th is 1.1. So it looks like our max value is happening at x equals 1. Where's our min value? It's happening at x equals minus 1/2. Okay, switch over to Desmos, see if the picture looks consistent with our work. You can always check your work or make sure it's consistent. So here you're looking at a graph of that function, h of x. And what do you think? Between minus 1 and 1, remember we're focused just between minus 1 and 1. Does it look like the smallest y value on that graph is happening right there at minus 1/2? Looks like it to me. The biggest y value on that interval was over here at the right endpoint at 1. So we ended up getting one of our extrema at an endpoint. It can happen. All right. Okay, so I hope those examples were helpful as you work on the homework and the activities in this section 4.1. You can practice this procedure. It's actually kind of a rare place in calculus, this method. Let me just flip back to the top of the screen here. Oh, you can't see this closed interval method, the author calls it. It's kind of a rare instance in our calculus class of this procedure that really, I mean, the details will vary problem to problem, but the procedure is always the same. Find the critical numbers, make a table with them and the endpoints, read off the minimum and max values. All right, thanks for listening.